Example 2 in 11.3 is really, it should be probably 3 different examples, but we're going to do them A, B, C. We'll just do a new page for each one. I think it's really important that when you see something that just says use the binomial theorem to expand, they do want you to find all the terms. We're going to do that really the same way we did the previous example. So I'm just going to write again that if I have 2a minus 3b to the power of 4, I could write this as 2a plus negative 3b to the power of 4. And the reason why I think it's important to recognize that is that we are comparing this to x plus y to the power of n. And if I look at those two kind of beside each other, I can identify that x in my binomial is 2a, y in my binomial is negative 3b, and n in my binomial is 4. And the reason why that's so important is our formula gives us the expansion in terms of x and y. And what we're doing is identifying that for this particular example, x can be replaced with 2a and y can be replaced with negative 3b. And n can be replaced by 4. And I want to do that just like I did in the previous example, that I could say now that term k plus 1, and we're going to manipulate k to find different terms, is equal to 4 choose whatever we make k times 2a to the power of 4 minus k times negative 3b to the power of k. And it's really powerful that what I wrote in b there is specific to this question. Above it in red, that term k plus 1 piece that I'm putting the asterisk beside, that is true for any binomial to the power of an integer. So what we're going to do is we're going to use the blue expression and we're going to find all of the terms. And I really would encourage you to ask yourself, how many terms would you expect? All right, now we're going to figure it out as we go through, because my first term, I'm going to make k equal to 0. So term 0 plus 1 is going to be equal to 4 choose 0 times 2a to the power of 4 minus 0 times negative 3b to the power of 0. That means that term 1, 4 choose 0 is 1, then it's multiplied by 2 to the 4, and it's multiplied by a to the 4. What's negative 3b to the power of 0? 0. So we don't even need to include it. So I'm going to say that term 1 is equal to then 2 to the power of 4 is 16, and then we have our a to the power of 4 in place as well. All right, that's the first term. We have 4 more to go because there's 5 terms in total. I'm going to kind of offset them just a little bit. So I'm now going to find term 2, which is when k is equal to 1. So that's going to be equal to 4 choose 1 times 2a to the power of 4 minus 1 times negative 3b to the power of 1. 4 choose 1 is 4. Then I have 2 cubed a cubed. And then I have negative 3 to the power of 1 and b to the power of 1. And this is where it starts to get a little bit, hectic. This is going to be 4 times 8 times a cubed times negative 3 times b to the power of 1. So we just write b. 4 times 8 is 32. 32 times negative 3, I get negative 96 a cubed b. And having, those coefficients within our binomial certainly do make these questions a little bit trickier. You just have to make sure you're really diligent with the brackets as you go, because we need to do this 3 more times. So I'm going to find term 3, which is when I make k equal to 2. So that's going to be 4 choose 2 times 2a to the power of 4 minus 2 times negative 3b to the power of 2. That means that term 3, I'm just going to put 4 choose 2 into my calculator quick because I don't know that off the top of my head. 4 choose 2 is 6. I'm going to be multiplying by 2 squared, by a squared, by negative 3 squared, and by b squared. That means that term 3 is 6 times 4 times 9, or 216 a squared b squared. Notice the pattern on our exponents is still holding true. All right, next up, we're going to find term 4, which is when k is equal to 3. That's going to be equal to 4 choose 3 times 2a to the power of 4 minus 3 times negative 3b to the power of 3. So term 4 choose 3 is actually the same thing as 4 choose 1. So that's 4 times 2 times a, they're both to the power of 1, times negative 3 cubed times b cubed. And I get that term 4 is equal to 4 times 2 times negative 27. I get negative 216 ab cubed. And then last but not least, we're going to have term 5, which is when k is equal to 4. That's going to be 4 choose 4 multiplied by 2a to the power of 4 minus 4 times 3b to the power of 4. So term 5 is going to be 1 2a to the power of 0 is 1, so I'm not even going to include it. Then I have negative 3 to the power of 4 and b to the power of 4. So term 5 will be 81. I better check that. 3 to the power of 4 is 81. So I get 81 b to the power of 4. Now, I'm going to write out that expansion now. We can say that 2a minus 3b to the power of 4 is equal to, and I know I just got rid of term 1, but I remember it. It was 16a to the power of 4. Term 2 was negative 96a cubed times b. Term 3 was plus 216a squared b squared. Term 4 was negative 216ab cubed. And then finally, term 5 is positive 81b to the power of 4. Now, this is a bit of a meaner question, I would argue. It's not very common that we have to do an entire expansion like this. You could achieve this answer by multiplying 2a minus 3 by itself 4 times, but I promise you it would take longer. Well, maybe not promise, but it would be very likely to take a lot longer than using our binomial expansion theorem. All right, let's do one that's a bit more typical, which is where they ask for a specific term. And really importantly, there's no way you want to expand 4b minus 5. That's just crazy. But I am going to do that same thing and write it as 4b plus negative 5 to the power of 6. Because if I compare that to x plus y to the power of n, for this question, x is replaced by 4b, y is replaced by negative 5, and n is replaced by 6. Now, to get the expansion, term k plus 1 is equal to n choose k times x to the power of n minus k times y to the power of k, and we want the third term. Well, if term k plus 1 gives us the third term, we know that k is equal to 2. So I'm going to take the value of x, the value of y, the value of n, the value of k, and I'm going to plug them in. And I'm going to say that term 2 plus 1, which is term 3, is going to be equal to 6 choose 2 times 4b to the power of 6 minus 2 times negative 5 to the power of, and we know what k is, it's 2. So term 3 is going to be equal to 6 choose 2, which I had on my calculator, but of course I deleted it. Let me pull it up again here. Sorry about that. So 6 choose 2 gives me 15. So this is going to be 15. I'm going to have 4 to the power of 4, b to the power of 4, and then negative 5 squared. I'm just going to do it right away. It's actually 25. So now I have to multiply 15 by 4 to the power of 4, then multiply that by 25, and I get that the third term in this expansion is 96,000 times b to the power of 4. Now that's a particularly tricky one, but the one thing I would like to show you is that if we looked at the expansions, term 1 would have b to the power of 6, term 2 would have b to the power of 5, and term 3 would contain b to the power of 4, which we saw our form give us. And I really want to stress that it is not a good idea to brute force these and actually multiply 4b minus 5 onto itself 6 times. That's overkill. That's not what this particular lesson is meant to show. All right, the last one is tricky for students because of how I'm going to write it. It is very, very beneficial to use negative exponents instead of a fraction there. So I'm going to say that instead of a squared minus 1 over a to the power of 5, I'm going to write this as a squared plus negative 1, oops, I did not mean to include that fraction. So I'm going to rewrite this again as a squared plus negative 1a to the power of negative 1. And then that's going to be the power of 5. All right, so what I can do now is the same thing I've been doing. I'm going to compare this against x plus y to the power of n, and I can say that x is equal to a squared, y is represented by negative 1a to the negative 1, and n is going to be 5. But the question says, okay, in simplified form, which is going to contain a? And they really should have put maybe a to the power of 1 there. And the way that we can find that is by using our expansion theorem. So term k plus 1 is n choose k times x to the power of n minus k times y to the power of k. And we're going to plug in what we know. We don't know k yet. So term k plus 1 is going to be 5 choose k multiplied by a squared to the power of 5 minus k multiplied by negative 1a to the negative 1 to the power of k. Now, this is probably the trickiest part of maybe the course, but definitely 11.3. We're going to manipulate that just a little bit, and we're going to use our exponent laws to do that. So I'm going to say that term k plus 1 is 5 choose k. Because we have a power on a power, I'm going to write this as a to the power of 2 times 5 minus k. Then I'm going to write the -1 separate, which is going to be the power of k. And then because I have a to the -1 to the power of k, that can become a to the power of -k. And maybe I'll show that if I had a to the -1 to the power of k, that's a to the power of -1 times k, which I wrote as a to the power of -k. What I'm going to do is I'm going to get all my a's kind of beside each other. So term k plus 1 is equal to 5 choose k times -1 to the power of k. And then I'm going to write this as a to the power of 10 minus 2k times a to the power of -k. But what do we do with exponents when we're multiplying a common base? We add exponents. So I'm going to have 5 choose k times -1 to the power of k multiplied by a to the power of the two exponents added together. And that's going to be a really important consideration, that because I'm adding them together, if I take 10 minus 2k and I add -k, I get 10 minus 3k. So that becomes the exponent on that a variable. Now, what's really important is that if we want to see where we have a to the power of 1, the only thing that controls the exponent on a is this piece of the expansion. So if I know that the expanded, whatever term I'm looking for, contains a to the power of 1, then a to the power of 1 must be found by a to the power of 10 minus 3k. Back in chapter 7, we learned if we have the same base, you can drop that base, and we get that 1 is equal to 10 minus 3k, which means -9 is -3k, which means that 3 is k. Now, what's really important, and I want to go back to the unsimplified one, and I know that that's kind of a pain, but I'm going to go all the way back to this one right here. I don't know if I'll be able to move it. Yeah, I'll just rewrite it. If I know that k is 3, and the reason I'm going back to that is I want to confirm that I've done it correctly. Knowing that k is 3, when I put that in, so term 3 plus 1 is going to be 5 choose 3 times a squared to the power of 5 minus 3 times -1 a to the power of -1 to the power of 3. If I've done this right, I should have a to the power of 1 in that term. So we're going to figure it out. Now, it is the fourth term. I dropped my calculator again. I'm just going to put in 5 choose 3 because I don't know it off the top of my head. Oops. So 5 choose 3. I get 10 multiplied by, and I'll write this is going to be a squared to the power of 2 multiplied by -1 cubed and a to the -1 to the power of 3. This can be written as 10 times a to the power of 4 times -1, that's what -1 cubed is, times a to the -3, or -10 a to the power of 1, because 4 plus -3 is 1. And if with that expansion theorem, we were able to find out which term contained, a to the power of 1 without doing the entire expansion. And, we just did that for a to the power of 1. What if we wanted the term that didn't have a variable with it? So the constant term. We could also be asked to find the middle term or the final term or something along those lines. And I really can't stress enough how powerful it is to be able to find a specific term in an expansion without having to do, honestly, it would probably take me, 5 or 10 minutes to do that entire expansion by hand. That would be a very, very ugly expansion to do without this binomial expansion piece. I know 11.3 is tricky. I fully understand that. We typically have a few days for you to master that, get used to it. This is the kind of full unmodified assignment. I am going to put a modified assignment up on Google Classroom to kind of show you how to focus for our wonderful little digital world finishing in June here. All right, good luck. If you have questions, please ask me. I can do a few expansions or a few of these questions. This is not an easy chapter, so don't get down on yourself if it's a bit of a struggle to begin with.